All right. So, like many of you, I like to use LLMs to help with all sorts of things that I need to get done. So last night, I came home, I was pretty tired after work, and I asked my favorite LLM to help me out a little bit. I asked it to help me clean the house, fold the laundry, and make dinner. Unfortunately, this didn't work, although it told me all sorts of things that I should do myself. So what I'd really like is so that next time when you have a request like this, there is an embodied system, a foundation model sitting in a robot that can actually do it and not just spit out a bunch of text at you about what you should spend your evening on. Now, fortunately, robot foundation models are quite an active area of research these days. This is an area that's fairly young, but it is growing very rapidly. Physical Intelligence, the company that I and my colleagues founded, has been working on this for over 2 years at this point, and there's some nice results. You know, this is a robot making coffee using an espresso machine for 13 hours straight, assembling boxes in a factory. Lots of folks are working on this. There are amazing results coming out from other companies, from academia, from many different places. And when I thought about what to speak about in this talk, I figured maybe instead of showing lots and lots of results, I would zoom in on a particular technical challenge with these robot foundation models and some ways that we can start addressing it. Because underneath all of the demos and all of the results, there is a big question. Why is it that with all these really nice results, we aren't seeing robots that can follow arbitrary prompts all around us today? So typically, when somebody does research on robotic foundation models, they might have a task like this. Put the corn in the pot. This is from the Bridge data set. It's a fairly rudimentary kind of research-grade robotic system, and it's doing the task. So that's kind of nice. But that's not really what we want. What we want is something like this, where the robot actually goes and cleans your house, and the prompt is not like, pick up these shirts and put them in the hamper. The prompt is, I've got guests coming this evening. Given that line of text, the robot should understand what it is that you want and act appropriately, meaning that you have to complete the prompt that specifies an entire job, not just an atomic task. And it's not just about instructions. You need to make a plan, and you need to generalize skills to the new context and really handle this correctly, including the context when your slides go out in the middle of the talk. Oh, wow. It does depend on the people in this room, yes. So anyway, where was I going with this? The command is also in context. So the fact that you've got guests coming, like the way you interpret that depends on what the robot knows about you and your home and all this other stuff. So the point is that there is a lot of grounding and problem solving that goes into making this work for real beyond just the one atomic task. Now, a really powerful tool for this is test-time compute. Hopefully many of you are familiar with what this does. In LLM world, test-time compute is how we can solve complex problems by thinking about them harder, generating more tokens. It's a way to solve harder problems, but it's also has a less obvious benefit, which is that it can break down an unfamiliar problem into more familiar pieces. So if you tell the robot, I've got guests coming, that maybe the robot has never heard you say that before, but it can process the text, semantically reason about it, and break it down into things that it can actually do, all the way down to like pick up this t-shirt. So you can endow robotic foundation models with test-time compute to get them to be better at problem solving. We started working on this a number of years ago, and the key here is that it's not just about solving a harder problem. Going from an observation to an action, the model can break down the task into bits that are more in distribution relative to other parts of its training data. So it can say like, hey, you're asking me to pick up this object. I've never done that before, but what I have done before in my web scale pre-training is localize objects and images. So maybe I can localize an object and an image and use that as a stepping stone. Break down an unfamiliar problem into more familiar steps. Here's an example of this in action. Again, this is a research-grade task. It's not particularly realistic, but it's kind of a nice for isolating the issue here. We're asking the robot to make the blue block the only thing on the plate, and obviously there's something sitting on the plate right now, and you want to react in a way that is correct, but also semantically sensible. Like you don't want to pick up the sushi and put it on the table because that's a little bit unsanitary. It's a toy sushi, but maybe the robot doesn't know that. So the sushi should go into a semantically appropriate container. And the reasoning trace here actually takes care of that and even figures out that the sushi might be a little unfamiliar to the robot, so it should actually output a spatial coordinate instead of directly relying on the action output to take care of that visual distribution shift. And then when we run this, the thinking trace is updated every few seconds based on what's going on, and you can see that this thing kind of does it. Now, again, not the most sophisticated or impressive demo, but more to isolate that particular bit of the problem. And of course, you can optimize these thoughts. Thinking models are most powerful when the thoughts are optimized with reinforcement learning. And here, again, reinforcement learning serves a dual role, which is it curates the task specification and turns it into something that is more familiar relative to the robot training data, which means that you could propose a number of different textual commands to break up a high-level prompt and pick the one that the robot is most likely to succeed at. A little example of this here in the top row, the robot was commanded to put the hammer on the plate. I don't know why you'd want that, but for some reason you do. Very unfamiliar out-of-distribution task. And if you use an off-the-shelf vision language model, in this case this is Gemini, and you ask it to do this task, Gemini doesn't know what the robot can or can't do, so it says, yeah, like, go ahead and put the hammer on the plate. The robot doesn't know what a hammer is or how it goes on the plate, and it messes up. After reinforcement learning, the model actually kind of spoon feeds the task to the robot, say like, oh, move a little to the left so that it's right over the hammer, and then when you tell it to put it on the plate, there's really only one option, which is to do it right. So reinforcement learning helps to bridge that distribution gap. Now, so far, we've talked about thinking in language, but that's not the only tool available to us. If you're like cooking a recipe or something like that, it makes sense to think through the steps in language. But imagine you're rock climbing. You probably don't think like, hey, I'm going to move my arm 37 centimeters to the left. And it's more natural to think about this spatially in terms of locations, in terms of what things will look like in the future. And you can have robotic foundation models that think in other modalities. Again, this is some older work in a kind of more researchy context, but we had some work on following instructions where instead of breaking down the instruction to text, you break down the instruction into an intermediate image. Essentially, imagine an image of what things would look like if you make progress towards the task. That's your thought. And then condition on that thought, it's easier to take the correct action. This works very well because, of course, the image generation can be pre-trained on lots of internet-scale data, associating language with images and enabling the robot to imagine substeps. So to bring this back to large-scale robotic foundation models, the last thing I want to tell you about is some recent work from physical intelligence on large-scale models that think with multiple different modalities. So this is one of the features of the Pio-7 model. It's a large-scale vision language action model that incorporates a lightweight world model into its decision-making process. So it reasons about a task in language and in images, and then grounds all of that down into actions. So here's a little demo we did. Here, Lucy is teaching the robot to use an air fryer. We intentionally made sure that we didn't train it to use the air fryer, so it's an unseen appliance that it has to generalize to. Out of the box, if you tell it to air fry the sweet potato, it actually succeeds, although it takes quite a while and kind of fumbles with it quite a bit. But if you give it a little bit of additional supervision, it can be much more reliable. And crucially, the supervision is not in actions. Lucy is going to talk to the robot in words and will actually explain the task step by step just by coaching it. And that adds additional data of images with language. The actions here are not ground truth. The actions are taken by the robot. And after this coaching, which is used to fine-tune the thinking process, again, there's no ground truth action here. It's just teaching the robot how to think, essentially. Now it can use these multimodal reasoning capabilities to do the task quite fluently. So what you're going to see is the text, which is now generated by the model itself, and you're also going to see images, which are intermediate thoughts that the model is generating to help it do the task. So here's the language thoughts, and underneath it is the image thoughts. And now the robot can do this sweet potato air fryer task pretty reliably. So that's kind of an illustration of how multimodal thinking can actually make for much more powerful robotic foundation models that generalize more broadly, even to new appliances that they haven't seen before. So some takeaways. Thinking or reasoning models can allow robots to generalize better and follow more complex prompts. And I think in the long run, that's going to be really important because we're going to want these things to follow much more elaborate prompts than what anybody is doing now. Prompts like, you're a robot butler, clean the house at 6 p.m., get dinner ready, do my laundry on Saturdays. Like, that's the prompt, and it might take the robot weeks of operation to fully do that. The thinking doesn't have to be in text. The physical world is complex, and you should use the right modality for the job. And I think that there's a lot of really exciting developments we'll see over the next few years in multimodal thinking. And we can even use multiple modalities simultaneously to think at the right level of abstraction, so that if you're following a recipe to cook, maybe that's in language, but if you're figuring out how to use a new appliance, perhaps you have to imagine where your hand should go to push the button or to open the container. All right. So this would provide both a way to solve harder problems and more effectively transfer knowledge from other sources that might be represented in different modalities. I'd like to thank both my students at UC Berkeley and my colleagues at Physical Intelligence who carried out most of this work, and thank you for listening.